Okay, sorry about that. You'll get a minus 5 minutes on the actual video. So we said that a deadlock is when a set of threads are all waiting for each other, right? I wait for an event. I was waiting for Jake to give up his fork. Jake was waiting for Hunter to give up his fork, and Hunter was waiting for me to give up my fork. And we were just stuck with that forever. Okay, so let's take another example where we actually make things a little bit clearer. Let's say we have two threads, T1 and T2. What T1 tries to do is we have two locks, S1 and S2. So T1 is going to try to lock S1, then lock S2. Then this is our critical section, then unlock S2, unlock S1. Okay, so next, T2 is going to try to do lock S2, then lock S1, and it's going to enter its critical section, unlock S1, then unlock S2. So can you give a ordering of these events that will lead us into a deadlock state? Yeah, you're good. Yes. So let's imagine that T1 has already locked S1, and then we have a context switch happening here. We go to T2. T2 will lock S2, so it will acquire the resource S2, and then it's going to try to get the resource S1, but it's going to end up waiting for S1. So we're going to switch back to here and end up waiting for S2. So we kind of have this loop going on between those four statements that leads us into a state of a deadlock where T1 is waiting for T2 to release S2, and T2 is waiting for T1 to release S1, and they're both stuck. They're both waiting, and nothing is happening. So based off of this discussion, let's try to come up with what conditions must be met for a deadlock to occur. So there are four conditions. Let's try to get, extrapolate from the two examples that we saw what these conditions are. So what do you think? Any ideas? Yeah.
If one process uses one lock as like its overarching lock, and the other process locks that lock inside of it, yeah, right before its critical section. If the lock is shared by two processes, but one process uses a critical section and the other one uses it as the overarching lock.
Yeah. So you're saying that something like this. This S1 is T1 is using S1 as its overarching lock, and at the same time T2 is using S2, or T2 is using S1 as part of its critical section, right? So that's a good point. And what we refer to, the condition that, or the term for this condition is called hold and wait. So this refers to T2's action. T2 is gonna lock T1 or lock S2, and then it's going to wait for S1 while still holding S2. So I will go into a waiting state while sleeping on a lock that I already own. Okay, so a thread requests and sleeps on a resource while holding another resource. So other conditions. Can you think of something else? If we go back to this example, or imagine going back to our forks and gaming example. I'm kind of hinting at it with the green circle. So a question for you is, how do you think the dependencies between the two threads are organized? Yeah.
Shouldn't it just depend on the order in which you're locking?
Yeah, so the order in which you're locking plays an important role, right? And when would that order of locking be problematic?
Locking all of them consecutively without unlocking?
Okay, so we're locking consecutively without unlocking. And how are the locks between the two processes interleaved, in a sense? So if you think back to this example, we locked S1, but before we locked S2, we jumped to lock S2, then we went back here. So how is the interleaving arranged? Yeah. Yeah, so the outcome of that context switch is what? In terms of like who's waiting for who? Yeah.
They're both waiting on each other.
Yeah, so we have this kind of circular dependency between them, right? T1 to move is waiting on T2. And T2 to move is waiting on T1. Okay? So that's the organization of the scheduling of those locking statements leads us to a place where T1 is waiting on T2, T2 is waiting on T1. So we have a circle, we have a cycle going in. So the second condition, we refer to it as a circular wait. Okay, so that happens when T1, let's say we have 4 threads. T1 waits on T2, T2 waits on T3, T3 waits on T4, and T4 waits on T1. Okay, does that make sense? Yeah.
I don't see the difference between the two.
It's subtle. So the trick is that while waiting for T2, you hold a resource that T4 needs.
So in hold and wait, that you can be in a deadlock just by yourself. You don't need to line on
It's both conditions must be met. So it has to be hold and wait and a circular wait. You can sometimes, so for example, in the readers and writers problem, we did a hold and wait, but there was no circular dependency. So the readers went in, and then at one point, we kind of slept on the lock for the readers when we wanted to prevent new readers from coming in, right? We did this lock, then if statement, then another lock, right? So we did a hold and wait, but because we don't have a circular wait or a circular dependency, there was no deadlock in that case. So one without the other is not going to be enough. It has to be both of them at the same time. Questions?
So both must be met for.
There's 2 more conditions that we're going to bring about, and all 4 of them have to be met for a deadlock to occur. So the third condition is called no preemption. So let's go back to our first little game example. If I was a very nasty individual, what could I have done to both either of Hunter or Jake to get their forks? Say that? Yeah, like just either beat them up and get the forks or do something along those lines, right? Why didn't we do that? Because there was no preemption allowed. So what this means is when a thread holds a resource no one can forcefully take it away. Okay. Now, fourth problem or fourth condition is what we refer to as mutual exclusion, which is the following: that anytime I hold the fork, I will hold on to it, and no one else can have it or do anything with it at the same time. Right? So when I access a resource, everyone else is not allowed to access that same resource. So it's kind of pretty much very linked to the fact that we don't have any preemption. Preemption says that in addition to that, no one can forcefully remove me from ownership of that resource. So if a thread owns a resource, it has exclusive access to the resource. Okay, so these are our four conditions that must be met for us to have a deadlock. And the trick is all four conditions, if all four conditions are true, then we necessarily have a deadlock. Okay? So, but we might have a circular wait without a deadlock. We might have a hold and wait without a deadlock. We might have mutual exclusion without a deadlock. That's pretty much the whole reason why we do semaphores and mutexes and all of that is to achieve mutual exclusion, right? And the fact that we don't have a preemption is not enough for us to actually have a deadlock situation. If you're familiar with some of the mathematical terms between necessary and sufficient conditions, those conditions are necessary but not sufficient. All four of them have to be there for the deadlock to occur. Okay, questions? So let's take a moment and think about how do we reason about those deadlocks and how do we reason about figuring them out. We're going to introduce what we call the resource allocation graphs. So in a resource allocation graph, we represent a box for the thread, circle for a resource, and then if we have an arrow from a thread to a resource, this means that call them T and R. T requests R, so it might be sleeping on R. And if we have an arrow from a resource to a thread, then we say that T acquires or holds R. Okay, so let's try to apply this to our first example with the two threads. We had two threads, so we had thread T1, thread T2. The way we achieve the deadlock is the following. We had S1 that was acquired by T1. So acquired by, let me draw a T2 here. And then T1 was requesting S2. However, S2 was acquired by a T1, and S1 wanted to request, or T1 requested S1. So, and that's how we got ourselves into a circular wait. Okay, so let's try and draw the resource allocation graph for the first game that we played, or the actual problem of the dining philosophers. So what do you think we need? How many boxes and how many circles? Yeah.
I mean, 10 boxes in it.
Yeah, in our case, we had 3 by 3, right? So for the dining philosophers, we had philosopher 1, philosopher 2, philosopher 3. And in between them, we had fork 1, fork 2, and fork 3. So what happened is, oops, P1, which let's say I was P1, I acquired my left fork. P2, which was Hunter, acquired his left fork. P3, which was Jake, acquired his left fork. Is that accurate? I think not. Left, yeah. This is left. So this way, this way, left and left. Okay. So P1 acquired the left fork F1, P2 acquired the left fork F2, P3 acquired the left fork F3. Now what happened is that I was requesting access to F3 because it's my right fork. P3 was requesting access to F2, which was his right fork. And then P2 was requesting access to F1, which was his right fork. And you can see that in this case, we also have a cycle in the resource allocation graph. And that's a general rule. Anytime you have a cycle in your resource allocation graph, means you have a possibility of a deadlock. So anytime, if you want to think about your resources, you can draw your resource allocation graph. And if you find a circle in your resource allocation graph, if you find a cycle in your resource allocation graph, this means that you have a very high possibility that you're going to end up in a deadlock state. Okay, questions? So how would you suggest that we solve this problem for the dining philosophers? Any ideas? How would we solve this issue?
So if I pick up a fork, you can take it away from me temporarily.
So one thing you can do is to allow preemption. So I'm gonna relax the rules and say you can fight for fork, right? I can forcefully take a fork from you, or you can forcefully take a fork from me, right? Hopefully that doesn't happen. Okay, so we don't want to like create these wars between the scheduler and the processes or the threads. Other thoughts? Yeah.
Set up like priority, like this one has priority, so if you can unlock if he's
waiting on something?
Yeah, so it's a good idea is that if we can play with the ordering, then we can actually break the cycle. So our problem was that we had a cycle in our dependencies. Well, if I come in and say, what if I break, let's say break this cycle somewhere, it means that I can get away from, I no longer satisfy condition 2, which said that we have a circular weight, and then I don't have a deadlock. So the ways to avoid deadlocks is to target one of those 4 conditions, either the Holden weight, the circular weight, the no preemption, or the mutual exclusion. So we're going to first tackle the circular weight problem by enforcing. In fact, what we're going to say is that for philosophers 3, pick up right fork before the left fork. So let's convince ourselves that this works. Let's redraw P1, P3, and P2. And we have F1, F2, and F3. Okay? So P1 first acquired F1, P2 first acquired F2. Now, P3, instead of acquiring the fork on the left, which is this one, they're going to try to acquire the one on the right first. So they will draw this arrow and wait on F2. In this case, I can go ahead and acquire F3. And here P2 is going to wait for me on F1. So now our circle is broken. Our cycle is broken. So by changing the ordering of things and enforcing a different order, we can actually break cycles. Once we break the cycle, one of the 4 conditions is not met, so we don't have a deadlock anymore. Okay? Questions? Yeah.
Which of the conditions is that targeting? Like, you're saying pick right before left.
Yeah.
That's just kind of like changing up the game.
Yes. So in a sense, we're trying to solve the problem by doing something that will allow us to avoid the deadlock situation. The end goal is not the rules of the game. The end goal is that we all want to eat, right? We all want to have the 2 forks and eat. So anything we can do to avoid the state where we're all just waiting and not eating is going to be fair game for us. Okay? Okay. So now I want you to go to your activity directory and look at the file abcd.c. There is a very similar problem to the dining philosophers. I will give you about 10 minutes-ish, depending on what time it is. Yeah, about 10 minutes to go through it and try to solve it. It's fairly simple. If you draw the resource allocation graph, you will be able to figure out exactly what you need to do. It's 2 lines of code. So, and let me know if you have questions.
art student with a circle.
Yep, there you go. That's how you. This is how you step talking. You could draw circles
Yes.
when you were a kid.
Not even possible. Yeah, so it depends on this. Yeah. Yeah. In a sense, just things you'll fix. It's that should be good. Okay. You can't really, unless you can say sleep. So when you say sleep, you want to add sleep, so it breaks down to the size of that lock.
Roll back.
Okay. I have 2 more minutes.
Yeah, just make sure you get right. You get to a verse one, so that they both confess, or if they both confess the same thing, they both inquire, so that one has to go first.
Okay, so, whoops. So I think it's pretty trivial to kind of go through that one. You can clearly see the cycles and the dependencies between them. You can try to fix that in whatever way that you think works. A small caveat is that you might not always get the deadlock, right? The scheduler is going to greatly impact how the processes or the threads behave, and whether you encounter the deadlock or not is, it's just as random as anything else, right? Now the problem is that you have to show us in your example, in your small paragraph that you have to write, that with your code, it's impossible to have a deadlock. So that your code prevents a deadlock from even happening. And if there was a possibility of a deadlock before, then your solution is actually gotten rid of that. Okay, so we have seen how do we avoid or prevent deadlocks by taking out the circular wait condition. We're gonna next tackle, whoops. We're gonna tackle the, there we go. Next, we're gonna tackle these two together because they're kind of pretty much aligned with each other. Okay? So what do you suggest we do to solve, to resolve, or to get around hold and wait or no preemption? What do you think we can do? So remember, hold and wait is when you sleep on a resource, waiting for a resource, but you already have another one in hand. No preemption is that if you sleep on a resource and you own another resource in hand, we cannot forcibly take it away from you. So any suggestions, how do we solve these two problems?
We're doing the 3 and 4 ones, right?
Yes, I think that was the number. No, it's 1 and 3. Hold and wait and no preemption. Yeah.
Is there any way to like stop context switches, like not allow the context?
That's a good idea. So to avoid this problem, we want to disable context switching. It's a really good idea, except the fact that we don't always have control over the scheduler, right? If you have root access, so if you have pseudo access, you can do something like that. But if you don't, then it's very hard for you to do. Yeah.
I think we could make it out an atomic function where it's then can't context.
You have atomic instructions.
Okay.
Yeah, so you have to be careful around, how do we use atomic instructions. But what you're saying is actually a solution to the mutual exclusion case, but we're not going to go there and do that today or in this class. Any other? Yeah.
Would you want to make sure that both are going to be available at the same time when you unlock them?
Yes, that's a good idea. So can we actually do something to make these two either I get all of them at once or I get none of them? Right? What do you use if you want to make sure that you either do one thing completely or you do nothing of it? Yeah. Yes. So one thing you can do is that you add another lock called deadlock prevention, DP. So before you do the locks on S1 and S2, you lock DP, you unlock DP here, and you do lock DP and unlock DP. So even if there's a context switch at this point, there is no way for thread 2 to enter here. Right? There's no possible way for thread 2 to get to this point because it will be stuck waiting on DP. So this way we're protecting our locks. So we're using a lock to protect our locks. So can you guess what the problem with this approach is? Yeah.
The order that you're unlocking.
Yes. So one thing you want to do is that probably want to move this here, but in this case they both work. So recall the usual condition that last one you lock is the first one you unlock. So it's S1, S2, S. Okay, yeah, that's my bad. S2, S1, yeah. Thank you, that was my bad. So what do you think might be a problem in this case? Not an actual problem, but like a penalty you're paying. Yeah. Concurrency. We're losing concurrency. So we're kind of, in a sense, serializing everything. We're saying even the locks themselves, we're gonna order them in a specific way. And then at that point, we kind of lost all the reason to do concurrency in the first place. Like, what's the point of doing multi-threading if we're just gonna do things serial, right? Doesn't hold any value anymore. So we don't wanna, we're just not using our concurrency anymore. So that is one way to get rid of these two conditions, but it's not going to be good enough, right? The other approach that you could use, there is a function called try lock, or if you're using semaphores, it's called sem try wait. And the way we employ it usually is we do something like this. While one lock S1, so let's say this is thread T1, then if try lock S2 equals false, so I was not able to try to lock S2, then I unlock S1, otherwise I break. So what do we mean? What does this mean? That I try to get, I lock my left fork. Then I look at my right fork. If it's not available, I don't sleep. I just put my left fork back down and I try again. Okay? So take your left fork, look at the right. Is there someone actually using that fork? If yes, if not, then you take it. If yes, then you just put your left fork down and try again. All right, just need one more minute. The problem with this case, if both of them are doing it, so lock S2, and then the same code here with S1 replaced by S2, we might end up in a condition called a live lock. So a live lock is compared to the case where you're trying to walk down a hallway and you move right and the other person moves left. They move left, you move right, and you kind of like enter this debacle of who's going to move forward. This is very similar. If the scheduler decides to actually always align us to the same execution, we might keep locking the same thing, unlocking it, locking the same thing, unlocking it, locking the same thing, unlocking it, and so on and so forth, and not making progress. So we're both active, we're moving, but we're not making any progress forward. Okay, so thank you for staying for the extra minute, and I'll see you guys tomorrow.
Yeah, like if you have two threads, at least you want the try lock on one of them, and the other one.
There are other types of solutions for live lock that we're not going to get into because it's not that much of an issue. Given enough time, the live lock is probably going to resolve itself out. Like you have to be very, very, very good at locking for a live lock to go for off, go on, whatever, right? So it's usually less of a worry than it is when deadlocks happen. There's no possible way to right?
So it's basically, if it happens, it'll cause a delay, but it'll still eventually resolve.
And it's going to be a pain to debug. Probably don't know why your code is taking this long, and it's random, right? Sometimes it might, sometimes it doesn't. So those are the tricky parts of this. But yeah, eventually it will work.
Because I don't feel like we have that.
Sure, let me know.
You know, you were gonna do UI.
Yeah.
She said she wants.
Sorry for the distraction about the other chat.
No, you're good. That's good. Actually, thank you for pointing that out.